नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे यूट्यूब चैनल केमिस्ट्री एकेडमी फॉर आईटी जेई एंड नीट. This is our problem series for JEE Advance. We are going to discuss the theory through problems. Hope this will be useful for all of you. I will request you to like and subscribe our channel. So the first problem is in the esterification of C2H5OH and acetic acid, an equimolar mixture of alcohol and acid taken initially yields under equilibrium the water with mole fraction of 0.333. Calculate the equilibrium constant. So it's a very simple question, but what we have to take care here, that in this reaction here it is written liquid, here also liquid, and here also liquid and liquid. So all the reactant and product are in liquid state. So it is a homogeneous mixture, there is no doubt in that. But when we have studied hydrolysis of ester, which is just a reverse reaction of this, then we write ester dissolved in water. So we'll write ester in aqueous state. Here water is acting like a solvent, and here the alcohol and acid form is also acting like solute. So there are three solute here: ester, alcohol, and acid, and the solvent is water. So water is assumed to be pure because it is present in excess amount. So when we write the value of equilibrium constant Kc, that is equal to the concentration of alcohol, concentration of acid upon concentration of ester. Because for pure water, the activity is assumed to be 1. So that will not come in this expression. But here, when we are discussing, water is not acting like a solvent. So when we write the equilibrium constant for this reaction, we can write that Kc for this reaction is equal to the concentration of the ester into concentration of water upon concentration of alcohol and acid. So in such type of question, be careful that what is written about the common, what is written in common bracket. If it is written in common bracket as aqueous, they are acting like solute, and if it is written liquid, 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 and liquid, it means that water is not solvent and they are not acting like solute. So now if I solve this question, they have mentioned that the mole fraction of the water at equilibrium, and initially it is equimolar mixture, so I can assume that initially a mole of alcohol and a mole of acid is there, and when this reaction will proceed in forward direction, I can write a minus x, a minus x, x and x. So in this reaction, you can see here that due to reaction, there is no change in number of moles. Here I am writing that at equilibrium, these are the number of moles, because delta n for the reaction is equal to 0. If 2x mole of alcohol and x mole of acetic acid consume here, then x and x are moles of ester and water is formed also, right? So if I write that what is the mole fraction of water, they have given that mole fraction of water is equal to 0.33, that is 1 by 3, which can be written as number of moles of water, which is x, upon total number of moles. So if you add the number of moles of alcohol, acid, ester and water, that is equal to the initial moles, that is 2a. So from here I can write that the value of x is equal to 2a divided by 3. So the value of a minus x is equal to a by 3. So now if I put the value, I can write that the value of Kc for this reaction is equal to concentration of ester. Since equimolar mixture is there, volume is not mentioned. Volume in numerator and denominator will cancel out. So we can write Kc in terms of number of moles. So the concentration or number of moles of ester is x and the value of x is 2a by 3. Then concentration or number of moles of water is x, which is 2a by 3. So I can write in terms of number of moles. So here it will be a minus x, which is a by 3. A minus x means a by 3. So if I simplify, a by 3 numerator and denominator will cancel out. So equilibrium constant for this reaction is equal to 4. So a very simple question, but be careful about this aqueous state and liquid state. Here water is not acting like a solvent, while here water is acting like a solvent. Moving to the next question, this is the most important example of Le-Chatelier principle. So very common in exams and very logical question it is, right? So let us go through the question first. Solid ammonium carbamate dissociate as, so the reaction is given, ammonium carbamate on dissociation will form ammonia and CO2 gas. In a closed vessel, sodium ammonium carbamate is in equilibrium with its dissociation products. At equilibrium, ammonia is added such that the partial pressure of ammonia at new equilibrium now equals to the original total pressure. Calculate the ratio of total pressure at equilibrium to the original total pressure. So here in the system, they are writing that solid ammonium carbamate is in equilibrium with its dissociation products. So dissociation of say ये equilibrium establish हुआ है. So initially ammonium carbamate is there and then it will start dissociating. And according to balance reaction, if 2 moles of ammonia is formed, then 1 mole of CO2 will form. So at equilibrium, this will be the situation. The number of moles of ammonia should be 2 times the number of moles of CO2, and it is happening in the same container at the same temperature. So I can say that the pressure of ammonia should be 2 times the pressure of carbon dioxide. So keeping that in mind, at equilibrium state, I can write that ammonium carbamate after dissociation, when it is in equilibrium, the pressure of CO2 will be P, then ammonia will be 2 times of P. So this is happening at a fixed temperature. I can write Kp for this reaction, that is partial pressure of ammonia whole square into pressure of CO2. So that is equal to 4P cube. The value of Kp only depends on temperature. So if you are not changing the temperature, the value of Kp is not going to change. So what we are doing now, we are disturbing the equilibrium state by addition of product. We are adding ammonia. So on adding product, this reaction will move in backward direction. And because of that, the pressure of CO2 is going to decrease. But whatever ammonia we have added, when the reaction is moving in backward direction, some amount of ammonia pressure is going to decrease, right? So in the question, they have mentioned that when further new equilibrium is established, the pressure of ammonia at new equilibrium state is equal to original total pressure. Original total pressure is pressure of ammonia at old equilibrium plus pressure of CO2, which is equal to 3P. So here at the new equilibrium state, the pressure of ammonia is 3 times of P. And we don't know what is the pressure of CO2. So we can say that the pressure of CO2 definitely should be less than P, because reaction is moving in backward direction. So this is pressure of CO2 at equilibrium. Now, if I try to simplify this, I can say that Kp is equal to 4P cube, which is equal to the partial pressure of ammonia at the new equilibrium state multiplied by pressure of carbon dioxide at the new equilibrium state. So I know that what is the value of partial pressure of ammonia. The partial pressure of ammonia at new equilibrium state is total original pressure, which is 3P. So 3P whole square. So from here I can calculate that what is the pressure of CO2 at the new equilibrium state. So on comparing this, I can write that this is 4P cube divided by 9P square. So this is 4 by 9P. So from here, I can write that the pressure of CO2 at the new equilibrium state is equal to 4 by 9 times of P, which is definitely less than P, original pressure, because if you add ammonia, reaction will move in backward direction. So now from here, we got that this pressure of CO2 is equal to 4 by 9 times of P, right? So now we can write Kp remains same, that is equal to 4P cube, because the value of Kp only depends on temperature. So now I can write that what is the total pressure at the new equilibrium state. So total pressure at the new equilibrium state is equal to 3P plus 4 by 9 times of P. So on simplification, I am getting this value is 31 divided by 9 times of P. So now if I put the value over here, I have to calculate P total at the new equilibrium state upon P total at old equilibrium state. So P total at new equilibrium state is 31 by 9 P, and P total at the old equilibrium state is 3 times of P. So P will cancel out. I can write this value is equal to 31 divided by 27. Very common question, but the concept is very beautiful, right? So you can see here that 2 points are important here. The value of Kp only depends on temperature. If you are not changing the temperature, value of Kp is not going to change. And on adding the product, the reaction will move in backward direction. Only those products or those reactants which are in the expression of equilibrium constant. Like in this question, if I add solid or remove solid by small quantity, there is no effect on equilibrium state. Reaction will not move in forward or backward direction. Moving to the next question. Additional solid silver sulfate is slightly soluble solid. Silver sulfate is a sparingly soluble compound, is added to a solution of silver ions and sulfate ion in equilibrium with solid silver sulfate. So already we have a saturated solution of silver sulfate, and now in this solution we are adding extra solid of silver sulfate. So here it is shown in the figure. We'll discuss, we'll come here later. Which of the following will occur? The Ag plus and sulfate ion concentration will not change. The added silver sulfate will dissolve. Additional silver sulfate will form and precipitate from solution as Ag plus ions and sulfate ions combined. The Ag plus ion concentration will increase and the sulfate ion concentration will decrease. So here in this, we have already a saturated solution of silver sulfate. So there is an equilibrium between AgSO4 solid and Ag plus and SO4 2 minus ion. So in saturated solution, we cannot further dissolve Ag to SO4. If we add some amount of Ag2SO4 solid, that is not going to dissolve. Here, they are asking that which of the following statement are correct when a saturated solution of Ag2SO4 is further supplied with solid Ag2SO4. So the first option is the concentration of Ag and sulfate concentration will not change because it is based on this equilibrium, and we know that the value of equilibrium constant Kc for this reaction is equal to the concentration of Ag plus ion whole square into concentration of sulfate ion. This solid is not coming in this expression, so we know that on adding or removing this solid, there is no effect on equilibrium state, means the concentration of Ag plus ion and sulfate ion is not going to change. So by this concept, I can say that the first option is correct. A is the correct option. Ag plus and sulfate ion concentration will not change. About the B option, the added silver sulfate will dissolve. There is no guarantee that whatever we have added extra, it will completely dissolve. Definitely, since equilibrium is dynamic in nature, so whatever we have added, some part of that will dissolve, and some dissolved Ag plus and sulfate ion will combine and come into the form of crystal. So if the question, the B statement is like that, if some radioactive Ag and Ag2SO4 is added to this system, do we find radioactivity in the solution? Yes, we will find some radioactivity in the solution, and that is telling that equilibrium is dynamic in nature. So here the first point which we should say that if radioactive Ag2SO4 is added, then we can find activity in the solution. It means that equilibrium is dynamic in nature. So there is no effect of addition and removal of Ag2SO4 from the system because Ag2SO4 is not coming in the system. But here, if we discuss that what will happen if I add water to the system, if I add a limited amount of water to the system, on adding limited amount of water, I can write that the value of the equilibrium constant Kc can be written as the number of moles of Ag plus whole square, number of moles of sulfate ion divided by volume to the power 3. So the volume is coming in denominator. So if you add water, if you dilute the solution, then I can say that Q is less than Kc. So here, if Q is less than Kc, then the reaction will move in forward direction. So the second point which is important for us, for the same question, they can ask that on adding water to the solution, more Ag2SO4 will dissolve. But again, there is no change in concentration of Ag plus and SO4 2 minus ion. So the concentration of Ag plus and sulfate ion is not going to change, provided we are not adding very large quantity of water. If we add some limited amount of water, the concentration of Ag plus and sulfate ion is not going to change, but more solute will dissolve, right? So that is one thing we should know about this. And so most of the time, if they are asking, they will say that addition of this solid is endo or exo. If they are not saying that, then if we guess, the best guess is that for ionic salt dissolved in water, most of the time the process is endothermic. So on increasing temperature, the solubility is going to increase. So these are some points which is related to this question. Be careful. More salt will dissolve. So the number of moles is increasing and volume is also increasing. So there is no change in concentration. Concentration is not going to change. It may possible that if I am adding AgNO3 to this solution due to common ion effect. Suppose if I am adding, this is a saturated solution and I am adding AgNO3. So due to common ion effect, this reaction will move in backward direction and solubility of Ag2SO4 is going to decrease. So we can write here that if we add AgNO3, then solubility of Ag2SO4 will decrease due to common ion effect. Question number